Perfect. So I'll also be talking about profiling, but this is about data profiling. I'll be talking about a new framework for data profiling using program synthesis. And this is joint work with the pros group at Microsoft, which is program synthesis using examples, and my advisor, Professor Todd Milstein. So just to give you an idea of why data profiling is an important problem to work on, we have a ton of data coming in at high speed and with high volume. So we have a lot of data being generated, and if we want to think about automated analysis techniques for this data, the key challenge is the variety in the data. So most of this data is unstructured, 90% of it is unstructured, and the data sets are incomplete in multiple formats or they're inconsistent. And so this project is about how do you deal with this data which comes in at high variety. For example, this is a data set containing references in multiple different formats. Some of them are PMC IDs, some of them are ISBNs and DOIs and so on. And I have highlighted in red the inconsistent formatting here. So the DOI may have multiple spaces after that. There are some records which are not available, and not all ISBNs end with digits. Some of them might end with the character X because it's a checksum. And if we look at what the state-of-the-art tools do on this data set, there is a tool from Microsoft called SSDT, SQL Server Data Tools. And pattern profiling is one of the features in SSDT, and SSDT generates a pattern profile which looks like this. It identifies that most ISBNs end with a digit, but it clubs the other ISBNs with not available and many different things into a dot star. So the profile is overly general and doesn't really help us get an idea of what the different patterns are. And if we look at another tool called Atacama 1, which only does profiling, it's a dedicated data profiling tool. Atacama 1 finds all the patterns, but the patterns are coarse-grained. It doesn't identify constants. It doesn't identify that some of these numbers, so n is a number here, d is a digit, some of these numbers are fixed width, meaning the wn here corresponds to something like the PMC ID, and the number is always 7. So there are 7 digits after a PMC. So there are no constants, no fixed width patterns here. And we propose this tool FlashProfile, which identifies constants, which identifies fixed width patterns, and it helps you identify all of the different patterns in your data without clubbing them to a more general pattern like dot star. So I'll explain in a minute how we do this. But just to highlight some other things that you might want from a profile. So a profile like this becomes almost unreadable at this point. It's too complicated, but the user who is familiar with the domain might want to define his custom patterns to get a more readable profile. And also, he might want to define patterns to find outliers in the data that don't match the data sets that the records that he expected. For example, he can define 2 patterns in this case called DOI and ISBN. Both of them he can define in terms of regexes in our framework, and he can get a profile like this, which show you have DOI and then 1 or more spaces, and then a DOI pattern which matches the expected pattern of the user. And it shows that there are no outliers according to the user's expectations. But we also want to allow users to drill into the data sets gradually. From this profile, we allow them to request 1 more pattern and get a profile which looks like this. So 2 things we want from a profiling tool. 1 is extensibility. The users should be able to provide their own patterns. The second is what we call interactive refinement. They should be able to refine the profile to whatever degree they want to. Okay, now I'll give you an overview of what typical profiling tools do, like SSDT or Atacama 1. How do they go from a data set to a profile? So typically what these tools do is they do clustering of the data set based on some metric. So they take a set of strings, cluster them into different partitions of strings, and then they learn patterns that describe each of these partitions. So at this junction of all of these partitions is your profile. And the clustering typically happens with a similarity metric, something like character-based, like edit distance-based similarity metric or something like that. And the problem here is if we want to allow custom patterns, the patterns are inserted at the pattern learning stage, at which point the patterns that you learn for partitions may not correspond to your partitioning. For example, if you have these 3 strings, face, fame, and 1, 2, 3, 4, would you like to club face and fame together or face and 1, 2, 3, 4 together? And the answer really depends on whether you have a pattern like a hexadecimal pattern. If the user provides a hex pattern and he prefers to see a hex pattern, like you give a cost function, I'll come to that in a minute. But the point is, if you have a hex pattern, then you might want to club face and 1, 2, 3, 4 together, but not the fame together, face and fame together. So then the question is, how do we make the clustering aware of the custom patterns that the user provides? Like before even we get to the pattern learning stage, how does the clustering know about all these patterns and partitions the data set in a way that is aware of these patterns? There are two key issues here. One is to find a similarity metric that is aware of these patterns. The second is, even if we have done the partitioning, how do we efficiently learn a description of the partition over an arbitrary set of patterns which are not known a priori? So the user gives me patterns, but I still need to learn patterns over them. And we show in this paper that inductive synthesis can help both these cases. The second case is obvious, more obvious I would say, which is pattern learning can be seen as a program synthesis process over an extensible grammar. So if you define a grammar for expressing patterns and you want to synthesize a program over that grammar, you're basically learning a pattern that describes a set of strings. The second case is interesting, which is you can define a similarity metric now using a preference or a scoring function for patterns. So typically in inductive program synthesis, you have many, many programs that are consistent with a small number of examples, but you disambiguate them using some scoring or a cost function. And we say that you can use this scoring function again to induce a similarity metric over your space of strings, and you can use it for clustering. So the key insight is this backward red arrow from pattern learning to the clustering process. So the key contribution here is we are solving an unsupervised learning problem, which is data profiling, but we're using a supervised learning technique, which is program synthesis. And in the paper, we formally define syntactic data profiling as a pattern-aware clustering problem, and we show how we can use inductive program synthesis to solve this data profiling problem. And we also show that inductive program synthesis allows for optimizations which you wouldn't otherwise have if you use metrics like character-based similarity measures and so on. We call our tool FlashProfile, and we evaluate its performance against commercial tools and research prototypes. And we show that it's accurate and performant over most real-life data sets. And one interesting application of data profiling that we show in the paper is not only do we use program synthesis for profiling, but it can actually go back and improve existing program synthesis techniques like PBE workflows, specifically FlashFill. So this is an overview of FlashProfile. In the default setting, FlashProfile just consumes a data set and generates a profile for you. Okay, and the profile, as I said before, the profile recognizes relevant constant strings and fixed width patterns. But you can additionally provide domain-specific patterns for your data sets, and you can control how many patterns you get in your profile. None of the existing tools allow you to control the granularity of a profile. Furthermore, you can also control the approximation accuracy versus approximation trade-off. We provide parameters to control for end users to control that. And this is now available as part of the Microsoft Program Synthesis Toolkit, Microsoft Prose Toolkit. We have a demo application on GitHub. The library is called matching.txt. It's not called FlashProfile. But the demo application shows how you can use the matching text API to profile your own data sets. Okay. So I won't go into the details, but I'll just give an intuition of how we do the partitioning and how we learn patterns. So this is a small data set containing ears. Some of them are missing and some of them are dirty, have characters after the ears. And this is what the clustering over the data set looks like. So we construct a hierarchical clustering, and for clustering we use AHC, agglomerative hierarchical clustering. So you construct a hierarchy like this, and at any point now you can cut this hierarchy to extract a desired number of partitions. So if a user requests 4 clusters, I can pick a height at which to cut this hierarchy tree. And the objective here is to minimize the cost of describing the generated partitions. So that brings me to the similarity metric, which is the similarity between two strings is the minimum cost pattern that you can realize within your pattern language to describe these two strings. And the only dependencies for the pattern over partitioning technique we show in this paper is one, a pattern learner, and two, a cost function over the patterns. We also show that for constructing a hierarchy like this, you do not need to compute a full dissimilarity metric over all strings. So just to give you an example, if I know a pattern that describes 1813 and 1898, I can probably reuse the pattern to estimate the similarity between 1813 and 1850, for example. So we show these optimizations in the paper. I won't go into the details. And the second optimization we show in the paper is how can you combine profiles over small chunks of data sets to construct a full profile over millions of records. So the second aspect is pattern learning or pattern synthesis. In the paper, we present a small pattern language, and we allow 4 kinds of atoms. Atoms are basic units, and the sequence of atoms is a pattern. We allow 4 kinds of atoms, each of which have slightly different synthesis strategies and optimizations. Character classes, regexes, functions, and constant strings. And pattern in this case is just a sequence of, it's an empty pattern or a sequence of atoms. And the nice thing about this language, since a pattern is just a sequence of atoms, is that you can recursively decompose the synthesis problem. So if you have a data set and you want to learn a pattern describing the data set, you can fix the first atom and then recursively solve the problem over the remaining suffix of strings for the rest of the atoms. And in the paper, we show that the synthesis technique is sound and complete over any given set of atoms that the user can provide you. And the cost function here is a trade-off between simplicity and specificity. By specificity, I mean how many strings you can match. By simplicity, I mean how large the expression is. So you don't want an overly complex pattern describing the data set, and you don't want an overly general pattern like dot star. In this case, the specific cost function we use is just a weighted sum over the individual atoms that your pattern contains. So I won't go into all of the evaluation and experiments we show in the paper, but one of the most interesting experiments we show is how profiling can improve PBE workflows, specifically FlashProfile. So in FlashProfile, typically what happens is you have a data set and you want to do some transformation over the strings. For example, in this case, you have birthdays and you want to extract years from birthdays. And if you have a data set like this, which has birthdays in 3 different formats, you would have to give many examples, or at least inspect all of the generated output and reach this particular birthday, which appears at the end of the data set, to conclude that all of the generated outputs are correct. If you had access to an input profile, I don't know if everyone can see this. If you had access to an input profile, we can profile the set of strings, and we can proactively request the user to provide an output from each of these classes. So for each of these classes, we ask the user to provide an input, and we show that you can actually construct the same program using less number of inputs, and without the user having to inspect almost all of the outputs in this case. So we actually did this experiment over all the FlashProfile benchmarks, and we show that in many cases, you require a lot less examples than the original FlashProfile required. Okay, and I'll be talking about performance and quality of the generated profiles from FlashProfile. So we measure quality by estimating how well does your profile generalize. So we take a small subset of your data set, we learn a profile, and over the remaining data set we run this profile, and we also run this profile over some randomly collected strings of the same size. And by doing this, we obtain some measure of true positives, false positives, and false negatives, true negatives. And basically the quality metric in this case is the F1 score, meaning you should not have a high false positive rate, but you should have a high true positive rate. And if we look at the plots, FlashProfile has really high true positive rate and really low false positive rate in comparison to SSDT, which has a very high false positive rate because you get a dot star in almost every single benchmark. And the other tool, Atacama 1, fails for many, many benchmarks for reasons unknown. Okay, profiling performance. So over real data sets, the first plot shows the number of strings in the data set, and intuitively we don't see a correlation here between the performance and the size of the data set, and intuitively that's because most real data set contain at most 4 to 5 different patterns, and if you profile small chunks and club them together, basically you wouldn't have to go through many iterations to find all of these different patterns. So if you profile a small chunk, it's good enough for the tool to guess what those 4 different patterns are. But we see a strong correlation here with the length of the string. That's because we reduce this, we do this recursive synthesis, recursive reduction for synthesis, and basically the longer the string is, the many more times you would have to do this reduction, and your profiling time would increase with the size of the string. But for most real data sets, we see that you can still profile them within 2 seconds. I won't go into comparison with every single related work, but we looked at a bunch of tools, both commercially available and some research tools, and we see that none of the tools allow you to provide your own patterns and refine profiles at the same time. Okay, so conclusion, we show that clustering, pattern-aware clustering or hierarchical clustering with program synthesis is a good way to do data profiling, and you can both refine your profiles and you can provide custom atoms for profiling your data sets. And there are many interesting future work to do in this direction. One of them is how do you set the appropriate cost for the patterns. Right now we set them manually by estimating how general a pattern is. But you can also machine learn these costs to optimize some quality metric for your profiles. And you can also refine approximation. Right now we do not do any refinement of the approximation. This is in the paper. You can see the details. But maybe you can apply some better approximation strategies. And finally, we only do syntactic profiling now, but you can imagine you might want to incorporate some semantic entities like names of people, names of countries, by doing named entity recognition from machine learning. Okay, so with that I'll conclude. Our tool is available as part of the PROS library from Microsoft. There is an example app on GitHub which shows how to use the API to profile your data sets. Thank you.
Hi, very nice work. So I have a possibly insane example. I want to know what you think about this. So imagine you wanted to make a profile for like a JSON protocol. And it seems like maybe your approach would work because you have this kind of hierarchical decomposition, right? So maybe it wouldn't totally explode, but is that something you could imagine doing? Like you watch data flowing back and forth and you look at the JSON and then you say, here's a nice profile for that data.
I think so. I mean, depending on how large these strings are, if these strings are small enough, I think you can do them. You should be able to do them in almost real time because we looked at strings which are almost 2,000 characters long and we can still profile them under 2 seconds. But yeah, I think you could profile JSON data.
Cool. Thank you.
Mm-hmm.
Any other questions? Very nice work. So I'm just sort of have some idea, like something. I think about the cost to measure the quality. So in the first talk, it's talked about improving the theoretical way to measure like conformity of the pattern. It might be something can be helpful with measuring the quality of profiles, basically.
Measuring the quality of profiles?
Yeah.
So the quality metric that I talked about only measures how well they generalize over the data sets that we saw. There is no guarantee about. There's no guarantee about how readable these profiles are or how small these patterns are. We only look at specific to a data set, how well does it generalize. But in terms of picking the cost, right now the way we pick these costs are by saying, if we take a random set of strings, how many strings will this atom match? For example, digits, how many strings will digits match versus how many strings will a dot, star, or dot match? Yeah.
I think this is why I think it has some opportunity to use like entropy, for example, like the first paper in this section, to measure this kind of quality.
Right. Right. Entropy or minimum description length or something. Yeah, okay.
Yeah, I was going to say pretty much the same thing, but no, I think it's an interesting question about, is this a different way to characterize the entropy of a set of strings than prior work? I mean, because you can talk about edit distance and things like that, but here you have a much more symbolic understanding of the structure.
In the paper we give specific examples of many kinds of edit distance and where they fail. So we compare with Jaro, Winkler, we compare with Levenstein distance, and there are tools which actually use these edit distance to do data profiling. Like Google has a tool called Google Open Refine, and they actually use character-wise similarity to do profiling, and the profiles are really bad.
Yeah, so this sounds like a stepping stone to actually reconstruct the way to think about collections of strings, right?
Yeah.
So, yeah.
Thanks.
All right, any last questions? If not, let's thank Sashwat again.
Thank you.